Okay, hello world. Welcome to iConnect Talks again. This is Miso Kim. I'm gonna be your moderator today. I'm a professor from Sungkyunan University, South Korea. I think there are so many people who've seen me already, and then I'm still your moderator. So today we're gonna have amazing two speakers who are iConnect Talks Young Rising Stars awardees. One speaker is Professor Tongchao Liu, and then the other speaker is Professor Matthew Jones. And then let's welcome our first speaker, Professor Matthew Jones from Rice University. And I'd like to introduce Matthew a little bit here. So Matthew Jones is an assistant professor of chemistry and material science and nanoengineering at Rice University. And the expertise of his research group covers the fields of inorganic nanoparticle synthesis, surface chemistry, liquid phase transmission electron microscopy, and nanoscale self-assembly. Matt is known for discovering an atomically-precise gold nanocluster as a precursor in the synthesis of anisotropic nanostructures and developing methods to assemble nanoparticles into chiral superlattice phases for the high-throughput fabrication of plasmatic metamaterials. So he's gonna share about these his research discoveries, and he's got so many fellowships, including an NSF and everything. And he graduated from the Carnegie Mellon University with BS degrees in both material science and biomedical engineering. He received his PhD from Northwestern University under the guidance of Professor Chad Merkin, and completed a postdoctoral fellowship with Paul Alivisatos at UC Berkeley before starting his independent career at Rice. And let's welcome Professor Matthew Jones. And Matthew, the stage is yours.
All right, fantastic. Thank you so much. Let me get my slides going here. Okay, great. You can hear this and it looks okay? Good. All right. Thanks, everyone. Thank you for inviting me. It's a real pleasure to be here. What I'm going to do today is tell you some of the work that's been going on in my group at Rice University over the past few years. And as you can see from this title slide, one of the things that we're very interested in doing is assembling new materials, creating new materials where our fundamental building block is not an atom, but a nanoparticle. And you can see these kind of beautiful superlattice structures that we can make. And the rationale for this is pretty straightforward. The idea is that we know that individual nanoparticles have new and interesting properties that are different from their bulk counterparts. So this is maybe one of the most striking examples. I'm showing here what a block of macroscopic silver looks like. Its color is silver, of course. And then on the right, what I'm showing are also silver zero solutions of silver zero particles suspended in a liquid. And you can see that the optical properties are now completely different and completely tailorable. And the way that we've done that is just by changing the particle size and the particle shape. So if the individual nanoparticles themselves have new properties, the hypothesis or the rationale is that these extended structures built from them will similarly inherit some of those new and interesting properties that we could tailor for whatever application that we're interested in. This is also appealing from a design standpoint. So I'm a chemist, and obviously we care about the periodic table. And if I went to one of the very talented chemists listening in on this presentation, and I started just, randomly picking, two elements on the table and saying, I want you to build a lattice or a molecule with this bond length and this coordination environment and so on, you would look at me like I'm crazy, because many of these combinations of elements on the table are incompatible or restrict the kinds of bond lengths you can get or the kinds of symmetries you can generate. That's because quantum mechanics is immutable. What's appealing about thinking of building materials from nanoparticles is that rather than an atom being our building block, if we have a collection of atoms or a nanoparticle, we can think of this as kind of a large atom or a meta-atom. And this is appealing because we have the inorganic core of our meta-atom being the thing that dictates the properties of our building block. And since all of these particles are decorated with a dense shell of organic ligands, molecules bound to their surface, It's these surface molecules which dictate bonding, how these meta-atoms will interact with one another. And so what I've done here in using this meta-atom analogy, I've conceptually separated the thing that dictates properties from the thing that controls bonding. And if you remember from our periodic table, that's very different from atomic building blocks. Once you select an atomic building block, it has a certain set of properties. You're now restricted to certain ways in which it can bond. And so the idea is that by thinking of a nanoparticle as an artificial atom, we can imagine an expanded periodic table where we have control no longer over just composition, but also particle size and shape. And we can now imagine mixing and matching different combinations of these particles and building structures that would never be accessible using atoms alone. So this is an appealing strategy. And as I've shown, we have some nice data showing these extended structures, but there is a problem. So this is maybe my favorite slide in the talk that illustrates one of the challenges in our field. So what I'm showing you here, these are all gold nanoparticles that are synthesized in my lab. You'll notice a few things. One, we have great control over the shape. So some of these shapes you'll be familiar with, like a cube or an octahedron. Others get, kind of exotic, like a tetrahexahedron. Doesn't matter. The point is that we have fantastic synthetic control over the particle shape. Second, you'll notice in these images, we also have great control over the uniformity of the particles. They're all approximately the same size. And that's really important for coaxing them into assembling into these extended superlattice architectures. So the thing that I'm not telling you on this slide is that the synthesis that we've used to generate all of these particles, the method, we have almost zero mechanistic understanding of how those syntheses work. We are essentially just following a recipe that's been published in the literature that was determined empirically, and we get out these particle shapes. We have almost no idea why one synthesis generates this shape and a very similar set of conditions generates this completely different shape. And so this is obviously a major problem. Imagine going to, the most talented organic chemist you can think of and saying, I want you to make this molecule, but I'm going to erase all of your knowledge of reaction mechanisms. It'd be crazy, right? But that's exactly the situation we find ourselves in nanoscience. We have target structures we want to be able to build. We have no mechanistic knowledge of how to synthesize particles for that target structure. So this has been an animating question in my research group over the past couple of years. How can we develop better mechanistic understanding of processes happening at the nanoscale, in particular, nanoparticle synthesis and assembly, in order to target our structures, our superlattices for a given set of properties? So this is what I'm going to talk about today. I'm going to tell a short story about some of the work that we've done in my group, trying to understand better, from a fundamental chemical mechanistic perspective, nanoparticle synthesis. So what I'm showing you here is a little bit more detail in how we synthesized all the beautiful particles I showed on the last slide. We're using a protocol developed over 20 years ago now by Catherine Murphy and Yuan Xia and several other people called seed-mediated growth or seed-mediated synthesis. And the premise here is really straightforward. It just says, these particles with these interesting shapes, they could be hard to synthesize in one step. So let's just split it into two steps. Okay, and the two steps are as follows. We start with some solution of gold precursors, a gold halide salt. We use a powerful reducing agent, and in the presence of a ligand, which is basically a soap, C is a carbon alkyl chain, N is the length of the alkyl chain, and it's a halide-based surfactant. So in the presence of this ligand, we reduce the gold salt, we generate small particles called seeds. Okay, that's the first step of the reaction. The second step is that we prepare something called a growth solution. It contains almost all of the same reagents. And this solution is kind of brought right to the cusp of being able to homogeneously nucleate particles, but not quite. So it's kind of kinetically trapped. And it is to that solution that we add the seed particles. So by providing existing surface, we get heterogeneous nucleation from the seeds in a slow and controlled manner. We get growth outward, and by appropriate selection of the surface chemistry, we can dictate what particle shape we get. So this is a diagram of what the surface is thought to look like. This will become important a little bit later. We have halides that are bound directly to the surface. The positively charged surfactants coordinate the negative charge of the halide, and these are synthesized in water, so there's a bilayer type architecture. Okay, so I have now summarized what is by far the most successful, ubiquitous, straightforward way of synthesizing really beautiful uniform nanoparticles. It's been going on more than 20 years. And for that whole period of time, these seed particles were described as 3 to 5 nanometer spherical particles. And kind of the amazing, surprising result out of my group is that we think these are actually a very special object known as a nanocluster. So let me be very clear about my distinction between nanoparticle and nanocluster. What I'm showing here is a plot of the energy of a particle. Think about this as just the stability. As we go up on this axis, we have particles that are more stable, and I'm plotting that as a function of the number of atoms in the particle. Okay, so this dotted line represents a bulk crystal. That's kind of the equilibrium state. And you'll notice that there are two distinct regimes on this plot. So this first regime, which I'm calling the nanoparticle regime, this function is just kind of smoothly varying at asymptotes towards the bulk as I add atoms. If I synthesize a particle of this size, if there's some particles with a few extra atoms and others with a few fewer atoms, they're all essentially the same energy. Okay, so the system can't differentiate a particle with 10,000 atoms and one with 10,001 atoms. So this partially explains why nanoparticles are intrinsically non-uniform. There just are not differences strong enough for the system to differentiate them. Okay, so these are nanoparticles. Clearly, in this regime of the plot, something very different is happening, and this is the cluster regime. So what this is telling us, let's take this data point, for example, let's say that's 20 atoms. This is saying that there is a particularly stable or favorable way to configure 20 atoms, but if I add one atom, or if I subtract an atom, there is no good way to configure 21 or 19 atoms. And so what this means is that if I target a synthesis for objects of exactly this size, anything larger than it is unstable, anything smaller than it is unstable, and I can therefore synthesize a solution of nanoparticles that are perfect. Every single one is exactly the same size, and they are therefore molecules. So these is a regime of nanoparticle molecules. So I should mention they are atomically precise, perfect, with respect to the gold atoms, the atoms in the core, and also with respect to the ligands that decorate the shell. So you can literally write out a molecular formula for these objects. So my claim is that for 20 years, people have been generating these seeds and using them to make nanoparticles, and they have been misidentifying them as nanoparticles when in fact they are nanoclusters. And obviously, knowing this and leveraging it is going to be very important for understanding the mechanism of these reactions. Okay, so let me tell you how it is we've come to that conclusion that these seeds are in fact atomically precise nanoclusters. So all I've done here is just rewrite the synthesis in a bit more general terms. We have our gold halide salt. Here I'm being just more generic about the name of this molecule. It is an alkyl quaternary ammonium halide. Okay, again, in water, the presence of a powerful reducing agent, we generate this structure. So if I'm right, and this seed is in fact a nanocluster, it is a molecule, which means that if I were to do mass spec, I should see a single peak of one mass, not a distribution of masses. And that's exactly what we see in multi-mass spec. So here's an example. We see this very large mass, 10,000. Now this is great. It proves that we're on the right track. There are molecules, some molecular species present, but this doesn't tell me anything about what it is, right? So we noticed, however, if we synthesize the cluster with this ligand, and then we just make a little tiny change. We just add a few carbons at the end of this chain, and we do the synthesis all over again. We get a larger mass, and we can show that these two objects are spectroscopically identical. So we think that means that the clusters synthesized with one ligand or another are identical, just the length of the alkyl chain is slightly different. So we can do this trick again, throw some carbon at the end of this chain, make it a little bit longer, do the synthesis again, you see the overall mass increase. Again, we can do it, we see the overall mass increase, and what you begin to realize is if I know the difference in mass of the individual ligands, because I'm just adding carbon, and then I measure the difference in mass of the overall cluster, I should be able to use that information to count how many ligands there are per cluster. So we decided to use this approach, and we just threw the kitchen sink at it. We bought every kind of alkyl quaternary ammonium surfactant we could find. Some of them we had to synthesize ourselves. And we found that in every case, using these surfactants, we generate the same spectroscopic signature of a cluster, but different masses. So this is a summary of those data. So what I'm showing on the y-axis is the mass of the overall cluster. On the x-axis is the mass of the individual ligand. If the anion is bromine, we get all of these points that lie along this beautiful straight line, the slope of which is 12. So that tells us that there are 12 of these alkyl quaternary ammonium surfactants per nanocluster. We can do the synthesis all over again, but just use surfactants where chlorine is our anion. We see exactly the same line with the same slope of 12, showing us there are 12 ligands. And then if you think about it, there's information here in the spacing between these lines along the y-axis that should tell me about how many halides there are per cluster. So it turns out that the spacing between these lines is exactly 20 times the difference in mass between one bromine and one chlorine atom. So that tells me that there are 12 ligands, 20 halides. If I then take all of these data points and subtract the mass of the halides so that they collapse onto a single line, and then just imagine moving with me along the x-axis all the way to the left when this line intersects the y-axis. So I've subtracted the halide mass. I'm allowing the ligand mass to go to 0. The only thing left in the cluster is the inorganic core. So that tells me that the y-axis intercept of this line should tell me how many gold atoms there are in the cluster. And so if I divide the intercept by the mass of gold, I get 32. So I've now identified all of the key features of my cluster, and I can actually write out a molecular formula for this. Gold 32, 8 halides plus 12 gives me 20, and then 12 of these alkyl quaternary ammonium surfactant ligands. So I just want to point out a couple things here. First, this is a heroic amount of work by my postdoc, Liang Qiao. On this plot are represented 48 unique clusters. And if you know anything about this field, you know that's extremely rare. It's often the case that you synthesize one new cluster and publish it. So this is a huge amount of work that went into this. I also just want to re-emphasize this is an amazing result. It means that for 20 years, we have been using a molecular nanocluster precursor without anyone ever knowing it. So, of course, we've struggled to work out the mechanisms of these reactions. We didn't even know what our precursors were, right? So this is all very exciting, but we wanted to get some corroborating data that supported these conclusions. So we do a lot of transmission electron microscopy in my group. The first thing we turned to was cryo-EM. So this is where we synthesize a solution of these seeds, then you flash freeze it as fast as you can. You trap in the structures that are present in solution, and then you can image it under cryogenic conditions. And so this is what one of those images looks like. So the first thing I want to point out is that we see nothing in this image that is 3 to 5 nanometers in size, which is previously what people had reported the seeds being. Instead, we exclusively see these objects that are about 1 nanometer in size, which is exactly what you'd expect for something with only 32 gold atoms. We are working on doing tomographic reconstructions using these data. We don't have that working yet. However, if we take these clusters and we deposit them onto a sheet of graphene, now there's no ice or solvent or anything present here, this is in vacuum, we can get these really nice high resolution atomically resolved images of our clusters. Now, we're not the first to attempt to image clusters with TEM. One of the reasons this is difficult is that many groups have observed incredible amounts of beam damage or beam perturbation, and we see that as well. So this is what it actually looks like when you're collecting these images. The clusters are rotating and moving, and they're extremely dynamic. And as a result, there really is no way, we think, to get structural information about the cluster from these images. The particle is too perturbed by the beam. However, we can still gather some really important data here. We can take advantage of the fact that the particle is rotating and sampling all of its different possible orientations for us at room temperature on its own. And so we developed a simple image processing algorithm that would find and count the number of gold atoms in each of these frames, and then just average those values for each of the frames. And therefore, we should be able to acquire a count for how many gold atoms are in each cluster. And what we find is that on average, we get something that is extraordinarily consistent with our mass spec data, that we have about 32 atoms per cluster. So that was nice corroborating data, but you may be thinking, and it would be a great question, how do you know that these clusters have been present for 20 years? Maybe you bought a bad batch of a reagent and you're the first one to make it. How do you know that it was there and being used for the whole 20-year period that this synthesis strategy has been used? So to address that, I went back to the first paper I could find that showed a UV-Vis spectrum of that seed produced here. And then I just extract data and plot it out. We just have a higher concentration of gold-32. So the peak here is just more pronounced, right? It's a sharper peak. We can see it a little bit more easily. So we think this is strong evidence that indeed these clusters have been present for 20 years and have been used in synthesis without anyone really knowing it. So thus far, I have identified the cluster and shown evidence that it exists and how many atoms it has and so on, but we have no information about the structure. So interestingly, in 2019, in literal back-to-back publications, two groups independently showed the first crystal structures of a gold-32 nanocluster, and those are reproduced here. Now, these clusters have completely different surface chemistry from the one that I've just shown you. They have triphenylphosphine or a bidentate amine ligand. In this case, there's a triethylphosphine and a halide ligand. Doesn't matter. These are not exactly the same cluster we have. They wouldn't be soluble in water and so on, but these two crystal structures agree almost exactly with respect to the structure of the inorganic gold core. So both of these reports show that their gold-32 cluster is hollow, has pseudo-icosahedral symmetry, a total of 20 binding sites for ligands, 8 of one type and 12 of another. So if you remember from the mass spec data, these are exactly the numbers that we got from our totally independent analysis of the mass spec. A 32 atom cluster, 20 total binding sites, 8 of one type, 12 of another. So we thought it would be extraordinarily coincidental if we didn't have exactly the same structure of our gold core in our case. And to corroborate that and to confirm that, we turned to two different theory groups to help us look at this problem. One was Rigoberto Hernandez at Johns Hopkins, who fixed the positions of the gold atoms in the core and allowed the ligands on the surface to relax in an MD simulation. And then once that had happened, we could truncate the ligands down to ammonia and then use all of those atom positions as inputs in a DFT simulation that was done by Andre Claiborne at George Mason University. And that DFT simulation now could predict a UV-Vis spectrum from a gold-32 cluster if it had this pseudo-icosahedral symmetry. So that's what's summarized here. In blue and green, we have the UV-Vis spectra of our gold-32 clusters. In black, you're looking at the simulated spectra, predicted spectra from DFT. And you can see that these line up fairly well, especially with respect to the strongest electronic transitions. And so we think this is excellent evidence that we indeed have this pseudo-icosahedral structure. I should also mention that you can, in DFT, simulate other configurations of gold-32 that are not icosahedral, and you find that those UV-Vis spectra do not match these. So I just want to take one short little diversion here and point out some interesting historical fact about what I've just shown you. So here's a bit more detail on the structure of the gold-32, the pseudo-icosahedral structure of the gold-32. It consists of a 12-atom core in an icosahedron that's hollow, okay? So there's no atom in the center here. And then there are 20 atoms surrounding that core. That gives me my 32. Now, because this object is icosahedral and hollow, people have termed it the golden fullerene. So not me, I didn't name it this, but it's been called the golden fullerene, and it is just cool that I'm at Rice University. I'm a professor at Rice University, where our chemistry department is well known for hosting 2 of the Nobel laureates for the discovery of the carbon fullerene, C60. So there's no reason why someone at Rice should be the one to discover that this precursor to nanoparticle synthesis is a fullerene, but it happened that way, and it is just a fun historical serendipitous moment that we've discovered that this golden fullerene is this precursor to synthesis. Here I'm just showing some low dose TEM images that show that the clusters, when matched with the crystal structure model, line up with the same 2, 3, and 5-fold symmetry axes you'd expect from an icosahedron. So the point here is just additional evidence that we're confident we have this icosahedral structure. Okay, so in the last 5 minutes, I just want to highlight what this discovery allows. So what makes this finding of a cluster precursor really exciting is that it is a molecule, and we didn't know that before. And it being a molecule means that it is now amenable to characterization by all kinds of classical chemistry tools that no one had really applied before. So here is just a simple example of a kind of experiment that we can do that was never possible before this. Here we're looking at ligand exchange between 2 different, very similar gold-32 clusters. So on the left here, this is a gold-32 cluster where all of the ligands have a 14-carbon alkyl chain. It has a mass shown here. This is a cluster where all of the ligands have a 16-carbon alkyl chain, and its mass is shown here. And then we take either one of these 2 clusters, and we add them to a mixture of the 2 ligands at different ratios. And we're then able to resolve every single one of the mixed ligand clusters. So 12 here, let's say 10 here represents 10 C14 ligands and 2 C16 ligands because there are 12 total binding sites. So what's really interesting is if you look at this middle panel here we have a 1-to-1 stoichiometry of the 2 ligands in solution, which means that if those 2 ligands bound the cluster equally likely, you would expect the distribution of mixed ligand clusters to be centered exactly halfway between the masses of the 2 pure clusters. So exactly halfway between this mass and this mass, i.e. where the gray bar is. And you can see that this distribution is not centered on the gray bar. It's biased towards the C14 ligand. So that tells us that the cluster prefers to absorb C14 over C16 ligands when given equal opportunity. And we can actually build a very simple 2-component Langmuir isotherm model to quantify this behavior. And here is an example of what we can do. We can't quantify absolute binding constants from this method, but we can get a ratio of binding constants. So we can now quantifiably say that there is a 5.5-fold preference for the binding of the C14 ligand over the C16 ligand. And like I said, this data wasn't available before. Now we can quantify the chemical properties of our precursor, use it in a synthesis, and then better understand why we got certain synthetic outcomes because we can rationalize what the precursor was. This is the same kind of experiment, except now the 2 ligands have the same alkyl chain length, and all we're doing is using a bromine ligand versus a chlorine ligand. And you can see, we'll take this panel, for example, we have 3 times as much chlorine as bromine, but all of the peaks are clustered towards the bromine cluster, which means it massively prefers to absorb bromine over chlorine. And the quantification for that is a 24-fold enhancement. And that's what you would expect from the binding of halides to metals, but still reinforces the point that this kind of quantitative data, which was never available before, I think will be very powerful in helping us understand synthetic mechanisms. Okay, one last final piece of data. You may be wondering, okay, this is great. You've proved to me this cluster exists. I like it, nice, but how do you know it's doing anything in the synthesis? What if it was just a spectator, right? It could be present, but it may not have any kind of important chemical role in the nanoparticle synthesis. So to address that, we prepared 2 syntheses of gold nanorods, seeded either with the original recipe for the seeds or with our new and improved recipe that contains a higher concentration of gold-32. So you'll notice just qualitatively, the nanorods look more uniform, more pure when we use gold-32 compared to the original recipe. We can look at the yield of rod-shaped products. We have more rods when we use our gold-32 compared to the alternative. And then this is a plot of the major axis versus minor axis of the resultant rods. So this blue ellipse tells you that the distribution of sizes is narrower, more tightly focused, so that the particles telling us the particles come out are more uniform. So I still can't tell you exactly how gold-32 is operating as a precursor, but this data convincingly tells me that it is playing some kind of operative role mechanistically, because increasing its concentration improves the quality of the nanorod product. So somehow it's playing a mechanistic role, and it is the subject of all my future career to try and figure out exactly how that's working. I'll just very, very briefly point out that this discovery of a nanocluster precursor is a somewhat general phenomenon. These are two examples of other kind of canonical nanoparticle systems, indium phosphide and cadmium sulfide, which have similarly identified atomically precise clustered precursors. So we think this is a rather general phenomenon for how precursors become nanoparticles. The future of my group will be to try and watch this happen in real time. This is a video of two gold-32 clusters fusing. This is something that we're really excited about, trying to understand crystallization at the 1 to 2 nanometer length scale. Okay, let me just wrap up really briefly. Okay, I'll go through this rather quickly. I've shown you that this very common synthesis is seeded by gold cluster precursors. There are still a number of very important questions we can't quite address, but again, that's good. I'll be employed for a while, right? It means I have more work to do. And I didn't get a chance to talk about it, but we can use these insights to better synthesize nanoparticles. A specific example are tetrahedra that we have shown can assemble into these beautiful chiral superlattices. With that, let me just thank all of the students who participated in the work, all the funding agencies. Thank you for your attention, and I look forward to the discussion time in a bit. Thank you.
Okay, thank you very much, Matthew. It was a beautiful presentation, and we can talk about it later further. Okay, let me briefly introduce our next speaker. So before that, I'd like to share my screen first. Yes, so our next amazing speaker is Dr. Tongchao Liu from Argonne National Laboratory. So he's also the awardee of ICANX Rising Star. And I'd like to introduce him a little bit briefly before he starts. So Dr. Tongchao Liu is currently an assistant chemist at Argonne National Laboratory. He has over 10 years of research experience in designing and synthesizing multifunctional materials for energy storage and utilizing cutting-edge characterization techniques to elucidate in-depth mechanistic understanding of the relationship between structures and performance, and to provide guidance and approaches to design and synthesize better battery materials with higher energy density and improved safety. So he's going to share his research about the lithium-ion battery today. And I'd like to emphasize that he has published a numerous number of papers, including Nature Energy, and Nature Nanotechnology, and more of that. So let's welcome Dr. Tongchao Liu here, and the stage is yours.
Thank you, Miso. Let me share my screen right now. Can you see my screen right now? Okay.
Yes.
Hello, everyone. Good morning, America, and also good evening, China and Australia. My name is Tongchao Liu from Argonne National Lab. I'm currently focused on developing the high energy density, longer cycle life lithium batteries. So today I would like to discuss some rational composition and the structure design to stabilizing the most common nickel-rich MC cathode materials. So first thing first, I'd like to acknowledge our funding support from DOE RE, and also our industry partner, BMW, Nissan, and GM. And our research topic actually covered most of area of lithium energy storage materials, including the cathode materials, electrolyte. Let me quickly find the printer. Here we go. And then for the next generation batteries, we do have the lithium oxygen and lithium sulfur batteries. Also, we are prepared for the future battery, that is all solid state batteries and sodium ion batteries. So I would like to have a little bit background for the lithium batteries, as not all the people have the battery experience. So the energy has been considered as the top 10 problems in the next 50 years, right? And the current world is mainly powered by fossil fuels, which unfortunately is irreversible and cause serious pollutions. So to eliminate our dependence on lithium on fossil fuels, the battery committee has dedicated to develop high energy density, long cycle life, and also cheap, safe batteries. Although the battery has been very, very successful, has been used many devices, including the small device and also the electric vehicles and the great energy storage. However, we still need much better batteries than today. Before I start the detailed topic discussion, I would like to give a very brief history and a milestone of lithium batteries. So the lithium battery technology is still very, very young. Actually, Professor Stan Whittingham firstly proposed the intercalation type recharge battery in 1970s. And following the Professor John Goodenough invent the first cathode material, lithium cobalt oxide, and then he paired the lithium cobalt oxide with the lithium metal that can double the capacity of the previous batteries. Following the Professor Rashid Yazami developed the anode materials, graphite. The graphite is still the most popular anode material in the today's battery technology. Following Professor Jeffrey Dunn reported the first lithium nickel oxide, that is the base on nickel, because nickel is much cheaper than cobalt. Just 1 year later, Sony and Dr. Akira Yoshino commercialized the first lithium battery in 1991. And then following, we have John Goodenough invented the lithium iron phosphate. That is another popular cathode using BYD electric vehicles. And 2 years later, Argonne developed the first lithium-rich AMC cathode, following the further advanced cathode using lithium nickel manganese cobalt oxide. And then in 2008, Tesla released the first electric vehicle, Roadster. And then 3 years later, AMC cathode get commercialized. Actually, Argonne licensed these AMC cathode materials to many companies. In 2019, the Nobel Prize recognized the contribution of John Goodenough, Stan Whittingham, and Akira Yoshino. Oh, sorry. I do have the video here. All right. So what is the working principle of a lithium battery? How can we combine this material together in the lithium batteries? So here, this figure shows you actually the lithium battery. You can transfer an electron from one side to another to complete the energy conversions. And the Atomically lithium battery have two active materials. One is anode, another is cathode. So for the anode, we do not have a lot of selection. So only have 3 materials currently. We have lithium metal, or we have the silicon, another is the graphite. As I mentioned, graphite is still the primary selection for most of commercial batteries, right? And on the another side, cathode, we really rely on a few structures, that is the layer structure AMC or the layered lithium cobalt oxide. And also we have the Symnel lithium manganese oxide, or we have the olivine lithium iron phosphate. Compared to the anode materials, cathode shows relative lower capacity, shorter cycle life, and also is very, very expensive. So to solve these problems, we need to understand what is the current bottleneck of the lithium batteries. The first one, or the major challenging of today's battery, is their high cost. Although we have seen cost decreasing in the last few years. Actually, the cost has reduced almost 5 times, but the current cell level cost is still 50% higher than the long-term target. And in addition, we have seen a slowdown in the cost decreasing trend in the last 3 years, with the cell levels cost even increasing in 2022. So how is it going of the cost? So when we look at the figure on the right side, we can find out the pricing of some key core materials has skyrocketed. For example, the price of cobalt and nickel remain really, really high in the last 3 years, and the lithium source, including the lithium hydroxide, lithium carbonate, their price has skyrocketed since 2021. So how can we reduce the price of a battery? We have to consider reduce the usage of cobalt and nickel, and also we need to consider how can we increase the lithium utilizations. To increase the lithium utilizations, that means we will need to deliver more capacity from the same conditions, right? Or how can we do that? So basically, for the lithium battery, there are many, many combinations for AMC cathode materials. So to increase the capacity, we had to have more nickel in the materials. However, in general, these cathode materials suffer from a trade-off between the capacity and the capacity retention or cycle life. So when we look at the figure on the right side, we can find when we have the 33% nickel, the capacity is relatively low, but the capacity retention is perfect. However, when we increase the nickel content to 85%, then we will have the capacity over 210 milliamp hour per gram. That is very, very high, but the capacity retention or the cycle life will drop dramatically. So to using the advanced cathode or higher nickel content, we had to solve this trade-off, right? And another challenge is we still cannot completely understand why this battery failed this fast. So many group has dedicated to understanding the failure mechanism of cathode materials, and these two aspects has been considered as the root cause. First one is the surface side reactions. So in detail, when we charge the battery to high voltage, the surface will be fully oxide to nickel 4+. The nickel 4+ is very active, will react with the electrolyte to generate surface side reactions. This process is usually accompanied by oxygen release, trace metal dissolution, and the irreversible phase transitions. On another side, the conventional AMC cathode has a secondary particle morphology. It is composed of a lot of primary particle. During the battery cycling, this primary particle will gradually separate with each other and then to form this particle cracking. Once this particle crack occurs, we will see the electrolyte get inside the particles and trigger the additional surface side reactions. So in our group, we have developed many strategies to solve the trade-off between the capacity and the capacity retention and cycle life. Also, we try to improve the safety of the current batteries. So we have developed 4 capacity of material synthesis. We have the different capacity of a reactor for the MC cathode materials. We can synthesize very dense the secondary particle and the primary particle. Further, we can have a different composition design. So, for example, this is a constitution gradient cathode. So the beauty of this cathode is this: we have the different composition within one particle. In the particle bulk, we can have very high nickel content to deliver high capacity. And then toward the surface, we decrease the nickel content. So in that case, we can stabilize the surface and they suppress the lithium, surface side reactions. And we further develop the single crystal cathode to remove all these particle boundary. In that case, we can suppress the particle crackings. And also to lower the cost, we have increased the manganese content in the cathode to have this lithium and manganese rich cathode materials. Besides the composition and the morphology design, we also developed some modification for the AMC cathode. For example, we developed the coating technology we call the P-dot coating using the gas phase. So here is today's timeline or the outline. So first I will discuss the cobalt-free cathode materials. Cobalt-free, we have removed cobalt from the cathode, then we can decrease the battery cost about 25%. And then we develop the concentration gradient cathode that can stabilize the AMC cathode and also extend the cycle life up to 6 times. We further will discuss the lithium-rich cathode for lower cost and the higher end density. For the future, we're definitely looking for some cathode has a less cobalt usage and also have high capacity, better cycle life. Okay, so firstly, I'd like to discuss the cobalt-free cathode. To remove cathode from the AMC, we had to understand what is the role of cobalt in the AMC cathode materials, right? We try to build up the linkage between the composition, structure, and the electrochemical performance. So we synthesize 3 comparable composition here. The first one is nickel cobalt 64. That means we have 60% nickel and 40% cobalt. And further, we decrease the cobalt to have this MC622. So that means we have 60% nickel, 20% manganese, and then 20% cobalt. We further remove cobalt from the AMC to have the nickel manganese 64. So we have 60% nickel, 40% manganese without any cobalt, right? And then we using high energy XRD and high resolution TEM to analyze the fine structure. So very interestingly, we found out the nickel cobalt doesn't have any structure defects like the lithium nickel disorder. Lithium nickel disorder is a very common structure defects in all AMC cathode materials. It will lower down the capacity and also block the lithium diffusion pathway. When we reducing cobalt with the manganese substitution, we will see the lithium nickel disorder will increase to 4.5%. And when we completely remove cobalt from the structure, we will have 7% lithium nickel disorder. And then here is the high resolution TEM. The bright spot are trace metals. And then we will look at this TEM. We can see this is the trace metal layer, and this is the lithium layer. Lithium is invisible in the TEM view, right? Because lithium is too light. And then when we look at the lithium layer, there's no trace metals. However, when we remove cobalt or we reduce cobalt to have the MC622, we can start to see some trace metal in the lithium layer, and then completely remove the lithium cobalt, we will have a lot of trace metal in the lithium layer. This is the solid evidence of lithium nickel disorder. So clearly, here we can conclude cobalt will suppress the lithium nickel disorder, but manganese will definitely increase the structure defects. And we further compare the electrochemical performance of these 3 materials to understand the role of cobalt on the electrochemical performance. Firstly, we found out the nickel cobalt shows the highest capacity is over 210, is really, really high. And then when we reducing cobalt with manganese, we can see the capacity drop a little bit to 200. And then we completely remove cobalt, we will have only 190. And on the other side, when we cycle this battery for longer cycles, we will see nickel cobalt dropped very fast because the capacity retention cannot, the capacity cannot keep at the high voltage. And then when we reducing cobalt to have more manganese, we will see the capacity retention improve a lot, right? From 70% to 86%. So clearly, cobalt will faster the capacity feeding, and then manganese can stabilize the electrochemical performance. So why the cobalt and manganese has such different role in the layer or the MC cathode materials? So to understand this, the mechanism, we are using many technology to evaluate these three materials. Firstly, we're using the in situ XRD to compare the structure evolution of three cathode materials. So in general, these three materials shows very similar structure change process. However, when we look at this O3 peak, you will see these three materials shows very different lattice parameter changes degree. For example, this nickel cobalt 64 shows a left shift for lattice parameter, a C-axis parameter, and quickly shift right. So this right lattice parameter, that means they will have a very fast or abrupt lattice construction in the high voltage. And then when we reducing cobalt with manganese substitution, we will see this right shift of a lattice parameter get reduced a little bit, and then we completely remove cobalt from the MC cathode. We will see very small peak shift in the high voltage. So basically, cobalt will trigger the huge lattice parameter changes, and manganese can suppress these lattice parameter changes. What's wrong with the lattice parameter changes? So you can image we have a particles. When the particle get expansion and then quickly construct at high voltage, they will generate a particle cracking. So in this case, cobalt will trigger more particle cracking, and the manganese can stabilize the particle and to suppress the particle crackings. We further confirm the detrimental effects of cobalt with another cathode materials. We synthesize the nickel cobalt 82. Usually when we increase the nickel content, we will see a faster capacity fading. However, here when we increase the nickel from 60% to 80%, we see the capacity retention get better than nickel cobalt 64. And then we further compare the structure evolution between nickel cobalt 64 and the nickel cobalt 82, we will see even with the increase of nickel, the structure construction will still get a decrease. That means cobalt will play an undeniable role on the capacity fading and also the structure evolution at the high voltage. So we further evaluate the morphology and the structure degradation of these materials. So this is the nickel cobalt 64. We can find out when we cycle after 100 cycles, these particles start to have some crack near the surface area, and also we have some layer gliding. So that is mainly caused by the huge lattice parameter changes. And also when we look at the high resolution TEM, so there we have started to see a lot of nanovolts. That is the evidence for the oxygen release. So that means beside the structure changes, this cobalt will also change the oxygen release from the lattice. We did the same observation for nickel manganese. We can find out manganese doesn't have any particle cracking, but also they do not find any the structure evolution over the long cycles. but the surface side reaction is avoidable because that is the reaction between the particle surface and then the electrolyte. So here we summarize the role of cobalt and manganese. Cobalt can suppress lithium-nickel disorder, and then cobalt will also trigger the huge lattice parameter and the oxygen release during cycling. That is the disadvantage of cobalt. On the other side, manganese can increase the lithium-nickel disorder, and then the capacity may drop a little bit. However, during the long cycle, cobalt can stabilize the structure to get better cycle performance. So we have say nickel manganese can be a very promising candidate for the cathode materials. So here we propose the nickel manganese acts as a next generation cobalt-free cathode, because when we remove cobalt, we can have much lower cost for the current batteries. And then we develop three cobalt-free cathode, that is nickel manganese alumina, lithium manganese titanium, and nickel manganese magnesium. Those three materials perform very well, much better than the nickel manganese and also nickel cobalt. So the next topic I would like to introduce is the new concentration gradient strategies. So as I mentioned, concentration gradient, we can combine different combination in the single particles. So here we do combine the different cobalt content and different manganese content in one single particles. So look at this particle, we have the constant nickel content close the particle, and then in the particle bulk, we can have a higher cobalt content, and toward the surface, we have high manganese content, right? And on the right side, we have a complete converse design. That means we have a high manganese content in the bulk and the high cobalt content in the surface. So we synthesize these two materials, it shows very similar particle morphology and also the structure properties. So we using the 3D X-ray fluorescence to confirm this morphology and this combination design. So look at this line profile. You can see manganese is very low content in the surface, and then it's manganese rich in the bulk. And then another one, we have a higher cobalt content in a higher manganese content in the surface, and then lower manganese content in the bulk. So we compare the electrochemical performance is these two materials, and also we add a baseline material AMC 811 that is a very popular or successful cathode in the current batteries. So firstly, we observe this nickel cobalt nickel manganese degrade very fast over the long cycle, and then the nickel manganese nickel cobalt perform very well. It's much better than the conventional AMC cathode, and also than the converse design. So we try to understand why this material performs much better, and then you can look at this DQ-DV curve. DQ-DV curve can tell you the structure reversibility of these two materials. You can see the nickel cobalt nickel manganese degrade very fast over the cycle, and then this nickel manganese still very stable over the long cycle, right? And then we further evaluated the morphology stability. So when we look at this nickel cobalt nickel manganese 82, you will see this particle will gradually crack, right? So you can see a lot of particle cracking near the surface and the bulk. So that means the electron will penetrate into this particle bulk and then trigger additional surface side directions. So we do confirm that we using high resolution TEM. You can see beside the surface side reactions, we also see some rock salt, the irreversible phase transition in the bulk. That means the electron will penetrate into the particle bulk. And then on the another side, the nickel manganese nickel cobalt shows much better morphology stability. So look at these three particles over 100 cycles. We didn't see any particle cracking inside the bulk, right? So that means the electron cannot get inside, and then we will suppress the surface reactions. So the reason why nickel manganese and nickel cobalt is much more stable than nickel cobalt nickel manganese is this: nickel cobalt shows huge lattice parameter changes, and the nickel manganese shows reduced lattice parameter changes. When you combine these two combination together, you will have, and when you have NCAM82, you will have a huge lattice parameter changes inside the particle that will damage the particle and have some particle cracking. However, when you have the nickel cobalt outside, they will have more space to release these particle lattice parameter changes, and then you will have better morphology stability, right? And the last topic I'd like to mention is the lithium and manganese-rich cathode. As I have mentioned, cobalt and manganese, cobalt and nickel are very expensive now. We try to increase manganese content in the cathode, and when we increase manganese into the cathode, we found out actually they will activate both cationic redox and ionic redox. That means we don't need to rely on the single cationic redox anymore. So these materials has much higher capacity. So the conventional or the single cationic redox cathode has only 140 milliamp hour per gram. However, these materials can deliver double the capacity. Right. So then we synthesize or design these materials. They has many structure characteristics. First, they has two structure domain. So these two structure domain are lithium metal oxide and the lithium 2 manganese O3. These two structure domain are structure coherent and electrochemically different. So, for example, we will look at the charge discharge profile. In the first charge, they have two charge platform. So the first, in the stage 1, we will active the lithium metal oxide below 4.5 volt, and then we will have a higher voltage platform for lithium 2 manganese O3. But the problem of these materials is, although it has a very high capacity, but it shows very fast capacity fading, right? Once you have capacity fading, you cannot manage this voltage, and then the electric vehicle will out of control. So at Argonne, we have developed many technology together to form this multi-scale characterization skill tools. So this technology can enable us to diagnose the battery from atomic level to microliter and even meter, and that will cover the characterizations from the lattice to the particle and even the device. So here I have one example. We're using multi-scale structure diagnostic tools to analyze the feeding mechanism of lithium and manganese-rich cathode materials. So we firstly using the EC2 XRD to monitor the medium particles structure changes. So we can look at the O3 peaks. We found out this peak is very reversible. During charge and discharge, this O3 peak will shift left, and then during the discharge, they will shift back to the original positions. So it seems that these materials are highly reversible, and they only have a single phase transition during charge and discharge. However, this cannot explain why this material degraded such faster, right? And then when we downsize to the tensor particle using EC2 CMCD, we have found out it's not a single phase transitions. They will have many phase transitions. So when we charge the high voltage to 4.47, we will start to see the second phase, and this phase actually is irreversible. And the following, when we charge to 4.8, we see a lot of the second phase. During the discharge, we start to see the third phase that is even unknown for the in the battery community. So clearly, the CMCD told me it is not irreversible. And then we downsize to one single particle using the BCDI. We can tell you why this material have the irreversible phase transitions. So when we charge the batteries, the red and the blue means the lattice string. You will see during the first charge, the particles start to have some the compressed string, and then when we charge the battery to 4.43 volt, you will see the whole particle has very serious lattice string. So once we charge to 4.43, we will start to see the second phase. And also at the same time, using the in-situ dams, we start to see the oxygen release. So clearly, the oxygen lattice stream will trigger the irreversible phase transition, and also will trigger the the oxygen release. So once the oxygen start to release and the structure start to changes, we will see the lattice string get released here. So we further down to the atomic level to indicate the real phase of the additional after the structure changes, right? When we charge to 4.5, we start to see the phase. So what is the phase? So this electron diffraction tell us, so when we charge the high voltage, we will start to see a layer, structure changes from layer to spinel. And once we have the spinel phase, we will see the lattice will displace, will occur the lattice displacement very seriously inside the particle bulk. And also over the long cycle, this the spinel phase will get more and more, and then this structure will degrade very fast. So now I'd like to summarize my presentation. We have the build up the synthesized capability for most of our AMC cathode, and then we build up the correlation between the composition structure and the electrochemical performance. We further propose the nickel magnetite X can be the next generation cobalt-free cathode, and we build up the new concentration gradient design to stabilize the nickel-rich cathode materials. It shows much better performance. And then the last topic we have discussed, we're using the multi-scale diagnostic tools to understand the failure mechanism of cathode materials. So for the next generation or the future battery technologies, so beside the lithium ion, we did develop the sodium ion batteries, because sodium is much cheaper than lithium, and sodium can use for the grid energy storage. Also, we are prepared for the solid state batteries. The solid state we can using the lithium metal as anode materials. Lithium metal is the has the highest capacity. When we have the solid state electrolyte, we were able to suppress the lithium metal dendrite. In that case, we can solve the safety concern of lithium metal batteries. With that, I think I can conclude my presentation, and also I'm happy to answer any questions later.
Okay, thank you very much. I'm gonna share my slide here so that we can have our face nicely. Okay.
It's a really good design, actually.
Oh,
I mean, these slides. I'm very impressive by these slides. You know, we can
yes.
show our, they have a table, right?
Alice and I can ask all this supporting team is doing great job. So
yeah.
Okay, so I think they are showing us together here. Probably me only now. So they're switching the screen later.
Oh, really? Okay.
So yeah, so we are gonna have for the next about half an hour. Oh, now we three of us are
here. We go.
Yes. So now we have a free time to discuss anything about your scientific findings, and then we can exchange some ideas about our career, and then you can give some advices to young scientists. Of course, you are a young scientist, but younger scientist relatively, yes. So do you have any questions for each other, or do you want me to start?
Oh, I have some scientific questions for Tongchao,
Yes.
if that's
Yes,
okay.
Of course.
So why did the price of lithium skyrocket in 2021?
Well,
yeah, it was very strange. It was like a huge change.
Yeah.
And I couldn't rationalize why that might have happened. Do you know why?
Yes, this is a very good question. When we look at the outside, you will see a lot of Tesla and also a lot of General Motor electric vehicles, right?
Mm.
So the electric vehicle expanded very fast in the last 3 years, and then this battery company start to generate a lot of batteries, and then that we will have the supply chain issue for the lithium and also for the trade metals. And then the lithium source now is only controlled by only few countries. So that is the reason why the lithium price go up very fast.
Mm-hmm. Okay. And how did you synthesize the gradient gradient particles that looked?
Yeah.
I didn't quite catch how you made those. That looked very hard, but maybe it's not.
Well, so for the material synthesis, that to be honest, that is the top secret in our group, and then also we have licensed this technology to a company. So basically, we will using the reactor we call the CSTR reactors. We pump trained metal to the reactor tank gradually, and then we can change the trained metal one by one. We can have 3, 4, 5, or even more trained metal composition using the different bottle, and with that we can pump different combination into the reactors. But the key is how can we control the different combination will grow in the single particle, right? So we will add some ammonia and also the little bit slow affinity rate to control the grow or the reaction speed. So in that case, these different combination will grow together in a single particle.
Yeah, rather than nucleating as separate phase-separated domains.
Yes, we still keep in the same phase actually, but the next generation will be the different phase within one particle. For example, the lithium cobalt oxide now it has been almost 40 years, so the capacity almost reached the maximum. The problem is this: we have the layer structures, and then we have a traded metal layer, we have a lithium layer, and then this lithium are part of the structure framework. If we remove 50% lithium from the layer structure, the structure is still very stable. However, when we force the battery to deliver a high capacity, we will have to remove more lithium from the structure, and then you can imagine when we remove most of this lithium out of the layer, this layer will start to decompose it, and then we will have the issue, right? So the next generation battery, I believe, we had to add additional phase to support the layer structure and also to stabilize the structure framework.
Understood. Yeah, that was very beautiful. I'm very jealous of all the equipment you have at Argonne. You have some wonderful characterization tools there. It was really nice.
Yes, we do have the user facility. So Matthew, you're very welcome to come to Argonne using our facility.
I've been there. We've done some work at Argonne. Not as extensive as you, but yeah.
Yeah, sounds good. And also, I come to another national lab, Brookhaven National Lab. You probably know that.
Yeah.
Brookhaven National Lab have a similar capability with Argonne, but Argonne now our synchrotron source APS has been shut down for upgrade. So now it is the third generation synchrotron source. They will upgrade to the newest generation synchrotron source. So we will have a 1 year's gap. So I come to BNL very frequently recently.
Right.
Okay, good. So speaking of the nice facilities, while I was looking at the in situ BCDI images Tongchao showed, that was the strain evolution of each particle. So I was wondering, so you might have so many different sizes of particles, so there should be a variation. So I was wondering how you could normalize this, like those particle to particle like sizes and morphologies. So you could watch one, but like there should be a variation particle to particle. Maybe I'm too ignorant.
This is a very good question. Yes,
I was just curious. So
So basically, we have this one experiment. We measure 3 particles because that is the in situ experiment. We cannot measure like a 50 particles because each particle measurement we will take like 15 minutes. So when we run the in situ, we can only measure 3. And then at least these 3 materials should show the consistent electrochemical performance and also the structural response, right? And then we can calculate the lattice parameter for each particles, and then we will compare the charge state with our, just the general particle in the coin cell without any in situ measurement, because the in situ measurement will have the very focused X-ray beam that may generate some beam damage, right, for the batteries. So we did check the charge state, and it matched well with the conventional battery in the lab. So I think we get convinced about ourselves. And also for the morphology, for the BCDI, we are running the 3 tomography actually. So that means we can get many slides for one single particle, and then we can combine all these particle together to have the 3D reconstructions. With that way, we were able to see the particle morphology and also the lattice ring. So the most of the particle, I would like to see all these particle shows the surface will have very severe lattice ring first, because most of the reaction will start from the particle surface, and then they will gradually expand to the bulk.
Oh, beautiful. So I think I have to echo what Matthew just said. So I'm getting very jealous now with all the facilities, and that's a fancy work.
We welcome you guys. You are very, the rising star in the field. I'm very happy to collaborate with you guys. And then we do develop many technology, not only the technology I mentioned here, also other technology. So yeah, we are very welcome to collaborate with you guys.
Okay, maybe I can make some excuse of going back to Argonne and then doing some experiment as an independent scientist, because before I used to be a student, so I couldn't have like that many opportunities. Okay, so do you have any questions for Matthew, Tongchao?
Yeah, for Matthew, I think Matthew have designed many nano materials, and then I'm very curious about the morphology design. How can you control the morphology to have a very specific, the particle shape? How can you do that?
Well, the way we do it normally is by controlling the surface chemistry. Right, because the particle, so the reason why you get a particular shape is that you have growth along one crystal axis that's different from growth along another crystal axis. And since growth is occurring at the surface, that's mediated by the binding of ligands, of molecules to the surface. Anything more specific than that about why you get a particular shape is really not well known at all. It really is almost completely trial and error. Yeah, people have just tried a bunch of conditions, different molecules, different things that cap the surface, and then they get out a particular shape. And there are some ideas as to why, and there are a few mechanistic components that are understood, but it really is just trial and error right now. And so that's one of the problems, is that it's very difficult to design a structure if you don't know why the particles form a particular way that they do.
Yeah. So, well, you consider using AI to, or the machine learning to learn how this morphology will change when we change the synthesis conditions, or using the different solvent or different formula for your synthesis.
Yeah, I mean, as I understand AI, what it would be able to do is show correlations between things, right? It would be able to look at a huge data set and then say, well, have you considered this set of conditions? And then you could try it. But it would never, at least right now, it wouldn't be able to tell you mechanistically why a set of
Right.
conditions, right? So, maybe someday when AI can do this, we won't have a job anymore if AI can do that. Right? But someday that might be possible. But right now, it would be very much like the trial and error approach that's done by humans.
Yeah, I completely agree. So we are recently discussed with the professor, they developed the AI technology. We try to using AI to monitor the particle growth and also the morphology changes. So we have many parameters, but it seems the AI is not ready to help us solve the problem yet. They do
Yeah,
can
I
provide
think
some, like Matthew said, can provide some like the database and can tell us some trend, and then we may able to align that direction to dig into the failure mechanism or the mechanism. But so far is still not that easy to use AI to power
Yeah.
all this technology.
Yeah, I think
Yeah,
of
I
it. I think of it. Sorry, Miso. Go ahead.
Oh, no.
I think of
You
it
can go ahead.
similarly to combinatorial chemistry, where you would run 10,000 different reactions, and then some would work and some wouldn't. You don't
Right.
know why. You don't know why some worked and some didn't. But then that gives you a target to go investigate, and then you can go do the detailed work on that system to figure out why. So in
Yeah.
that sense, AI could be helpful in pointing us in the correct direction, and then we could do the work of figuring it out. But yeah, agreed. It's not equipped yet to really explain everything.
Right.
Yes, one of the AI techniques you might be interested in is like active learning. So active learning is the algorithm that you can use when you have like a smaller number of sets of experimental data. But like the thing is, as Matthew said, we cannot know the mechanism. They cannot provide the physical mechanism or the understanding. But what they can do, it can do it. Provide is that they can provide some like optimal processing conditions out of the like a small data sets of experimental sets, and then so that we can get the feedback for our next experiment. And then that's what we can do, but not yet about the physical mechanisms yet.
Right.
So
Right.
let's see what happened later
Yeah.
in the next few years.
Yeah.
Yeah. The world changing very fast.
Yeah, so sometimes I feel a little bit like intimidated. So because every day something new comes up, and then I feel like I'm not following properly sometimes. So yeah. So how do you feel about the AI thing with your research in correlation with your research?
So far we do not have too much AI. At least in our lab, we are developing a battery, and we developing AI technology, but we haven't get together for all these to generate the better batteries materials. But now what AI can do for us, they do a very good reference literature review for us. They can just quickly pick up which reference what we really need, and then that will solve a lot of times for us.
Oh, what do you use for that? Is there a specific?
That is the one our collaborator developed.
Oh,
It is not the commercial one.
okay.
Yeah, also they can do like the structure screening for us from the literature.
Okay. So Matthew, are you applying any algorithms like of AI or machine learning to your research, or?
Yeah, we haven't really pursued that too much. One of the areas where I am interested in doing that is, I didn't talk about it, but we do some liquid phase TEM.
Oh,
So
okay.
this is a technique where you trap a liquid in a sealed cell that has really thin windows, so the electron beam can still pass through everything. And so you can get dynamics, you can get dynamic information. One of the problems is that, if you're using a very nice TEM and a good camera, a single image can be a gigabyte. So if you
Right.
take, and these detectors can generate, like 10,000 images a second. So do the math in your head. You very quickly, with one video, get terabytes of data
I
that are
know.
just like impossible to sift through. And there's some really fantastic work showing that conditions that a human being looking at the screen couldn't see anything. You wouldn't be able to see a particle. The electron dose would be too low. But if you do AI image processing on the big data set, you can get really nice high resolution data. So it implies that, there are imaging conditions where a student sitting at the instrument can't see anything, but the data is still there. And so what I'm interested in doing is seeing if we can develop models that can do the image processing on the fly while you're sitting at the TEM. That's going to require a lot of computing power and probably some AI optimization. But we have a big data problem, basically.
Right.
And I think AI could be really helpful in sifting through, finding where the important data is, getting rid of most of it, which is not useful. It could be really helpful for that.
Okay, intriguing. So going back to Matthew's work, so I was wondering about this specific number of 32. So that should be a 32, right? So like I'm a little bit ignorant about this, but like the 32 number, but other numbers, would that be any other meaningful thing? So I don't know how to formulate the question from here. So
what's
32
special about 32?
Yes.
Why 32? Why not 33?
Yes. Thank you.
First of all, there are many different atomically precise clusters that have been found, that have been synthesized, ranging from, I don't know what the smallest is. There's like a gold 11 cluster and they go all the way up to like 200, 300 atoms. And so these are sometimes called magic number clusters. And the rationale is, it turns out that these clusters have electronic properties that are very, very much like SPDF orbitals in an atom, but they're called superatomic orbitals in the cluster. And so just like in Gen Chem, you would learn that an atom that has the D band completely full is really stable. You have a cluster that has the superatomic orbital that's completely filled. That's a very stable configuration. And so that's why you have this sequence where 32 atoms is stable, but 33 isn't. It's analogous to electronic structure in atomic systems.
Oh, thank you. It's clarified now, so I understood. So thank you.
I should also mention that the ligands bound to the particle can donate or withdraw electrons. So that count, that magic number count, depends on the surface chemistry, which is why, I don't know, there's like dozens and dozens of these, because the ligands matter and the structure matters. So but it's an electronic structure kind of argument for why you have stable clusters.
Yeah, I like the word magic number, so I keep that in mind.
Okay. Yep.
That's one of the take-home messages for me. So, okay, so my last questions for you, to both of you, with the advice. Would you have any? Would you want to provide any advice to the younger scientists or students? So to become an independent researcher, and then like what would you say to your student or any other student all around the world?
Matthew,
you want to go first?
Okay, Matthew, you can go first.
I'll go. Okay. Oh, I'm going first. Tongchao needs more time to think about the question.
This is a difficult question. So
it's a very difficult question. I guess the thing that I have found in my career that has been really effective is basically curiosity-based research. So often, the things that work, some of the best work that's out of the group, the best publications, are things that we did not set out to do exactly the way it looks in the manuscript. We set out to do one thing, and then as we were doing that, we noticed some interesting results, and we just said, "Oh, that's cool. What is that? Let's go explore that." And some huge number of the successes that I've had in my career come from that kind of that curiosity of just saying, "Well, why the hell did that happen?" And then exploring it. So much good science came from that approach. I think we just need to acknowledge that most human beings are actually pretty bad at science, right? And sometimes you just have to be curious and let the universe tell you what's interesting. If you're studying something and it's not working, but there's this one little observation that's interesting. You go, what is that? That's weird. Maybe that's a sign that that's the thing you should be studying, not the original project, and just be open about whatever it could show you. That has been really successful for me.
Yeah, I'm so totally with you. So yeah, curiosity-based research. Unexpected results.
Yeah. So for me, to be honest, I'm still in a very, very early state of my independent research. And then, so two things I think I do want to emphasize. The first one, just consider your research or consider your work in a different way. Don't trust the reference or the literature too much. You can always find the different phenomena. And then also don't just follow others' work. We need to jump out of the box. We need to consider what is really new. I think most of high impact journal like the work at Science Nature is not about how many work you did. It's about how advanced or how novel of it is your research, right? And this is the first one. The second one, I do benefit from the global collaboration. When I work at Argonne, I build up many collaboration with China, with the different national lab. I have a collaboration with 5 national lab and also many universities. I think that also very support my career and also for many publications.
Yeah, I always keep saying to my students that be suspicious on everything you've read in the literature. So
yeah, I agree with that.
Yeah. Okay, thank you so much for your beautiful talks. Literally, your slides were beautiful, both of you. So thank you so much. And then now it's time to deliver to you this online version, the virtual version of this certificate. So we are so proud of you, and big congratulations again on winning the ICANX Young Rising Stars. And then this is for Matthew, and then Alice, Professor Haisha Chang will send you the other certificate by email later. So thank you, Matthew, so much, and then big congratulations.
Yeah, thank you so much. It was a great opportunity.
Okay, and then Dr. Tongchao Liu, so this is yours, and then we are very happy to have you here, and we would like to have you back again as a young scientist again, and then now a mature scientist again, so like forever. So at ICANX Talks, and then thank you so much for giving a great talk, and then big congratulations again.
Thank you so much. I really appreciate it.
Okay, now let's say goodbye so that we can have a nice Friday. And then let me briefly introduce the next week's talk here. So we are going to have another talk next Friday. So let's come back to listen to these amazing talks again. And we are going to have so many people here. So, and let's meet again next Friday. Okay, that was ICANX Talks. Thank you so much, everybody. Good night and have a great day. Bye-bye.
Okay.
不再是奇迹，不再是幻想，此刻真感觉全世界对我鼓掌，不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。 什么可以阻挡心中无限的力量。I can, I can， 你也能够像我一样飞越最高山岗。I can, I can， 没有什么可以阻挡心中无限的力量。I can, I can， 你也能够像我一样飞越最高山岗。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can, I